When you completed this lesson, you should be able to identify ordered pairs in the Cartesian coordinate system, read and interpret line graphs in real-world scenarios, and draw graphs from a given table of data. Photonic technicians need to know how to read, draw, and interpret graphs, and you'll work with graphs on a Cartesian coordinate system to do that. You may know this as an XY graph or a Y versus X graph, and real-world examples don't, however, usually come with Y's and X's, so you may encounter things like an oscilloscope, voltage, V versus time, T, or graphs of a laser cavity parameters, G1 versus G2, or graphs of laser beam irradiance, I versus position X across the beam diameter. Here's an example scenario that you may encounter as a photonics technician. You have a graph of a beam power versus the ratio A over W, which is the measurement of the size of the aperture that the beam is passing through, to the beam spot size, W, as shown here. And you may have to know how much laser power gets through a circular aperture when the radius A equals the beam spot width. Otherwise, A over W is equal to 1. Or for a laser beam spot size W, what is the ratio of the radius A to the spot size W if only 50% of the power is getting through? Or what is the minimum value? What is the smallest A can be in order for all of the laser beam power to get through the aperture? These are the kinds of questions that you might have to answer working with your lasers as a photonics technician, and we're going to learn how to do that in this module. As usual, we'll return to answer these questions after strengthening some of your skills. Consider the two explanations below for using a 3-prong plug adapter. Clearly, the picture is worth 1,000 words. You'd much rather look at the photograph or the drawing to find out how to use a 3-prong plug instead of reading word for word the directions. So that's what a graph is for. A graph will help you identify trends in the data, such as increasing or decreasing, or reaching a maximum and falling off. And that's where a picture can be worth 1,000 words compared to a table of data. The Cartesian coordinate system was developed over 350 years ago by a French soldier named Descartes. Now, it started with a simple number line graph. Now, this is something that you've probably seen in elementary school, so you're really familiar with it. From negative numbers out to positive numbers with a 0 in the middle. So we'll call this our x-axis. And you know how to locate those values on a number line. For example, x equals 2. Or x equals negative 3, or if x equals 0. 0 is also known as the origin, or the 0 point, and that's a terminology that you'll need to become familiar with. The x value specifies the horizontal position on our coordinate plane. Then we'll draw a second number line and orient it perpendicular to the first, crossing at the origin, y. Well, the vertical number line is labeled the y-axis. We can locate values on the y-axis too. Y equals 5, or y equals negative 2, for example. And we can identify points that have both an x value and a y value. For example, x equals 4 and y equals 3. Together, we'll call the two values an ordered pair. That's a term that you're going to have to be familiar with and use frequently in this module. An ordered pair specifies both x and the y value, as we've said in the previous slide. So we have x equals 4 and y equals 3, and that's going to help us plot the point xy equals 4, 3. So every point on the Cartesian coordinate system can be identified by an ordered pair of x and y values everywhere out here. The x value, or the first number in the pair, specify how far left or right you want your point to be. And the y value, or the second number in the pair, specifies how far up or down you want the point to be. Example 2 asks you to identify the ordered pair for a point A that's out there on the Cartesian coordinate system. So first find the x value by finding out how far A is over from the y-axis. So how far over did you have to go? In this case, we went 3. And so the first part of the ordered pair is 3. That will be the x value. And then the y value, how far up that point is. And you see that we moved the point up 2 units. And so our ordered pair is 3, 2. So we'll say that A is equal to 3, 2 as an ordered pair. Similarly, for point B, first find the horizontal distance, 2, and then find the vertical distance, 3. And so the ordered pair for B is 2 and 3. Continuing example 2, you'll notice an important difference between the ordered pairs A and B. A is 3, 2, and B is 2, 3. The order makes a difference, and that's why we call it an ordered pair. The first value is always the x-coordinate, and the second coordinate is always the y-coordinate. What ordered pair would you write for point C? The answer is -4, 1. You have to go x first is -1, 2, 3, 4, -4. And the y value is just up 1 unit. So that would be +1. Here's some more points. Can you identify their ordered pair values? Well, here's the answers revealed. If you didn't have time to get them all, you can just back up the video a little bit and try to look at it again. D is -3 over and -3 down, so it's -3, -3. E is over x, 4, and then down 2, so it's 4, -2. F is another one at the top corner here, and it's over 1 and up 4. So it'll be 1, 4. Notice the signs of the x and y values in our example ordered pairs. We have examples that are both positive, and we have examples that are negative and positive. We have x's that are negative and y's that are negative, and we have y's that are negative and x's that are positive. The Cartesian coordinate system is actually divided into 4 quadrants because of those signs that you see on the numbers. The traditionally numbered quadrant 1, Roman numeral 1, Roman numeral 2, Roman numeral 3 for quadrant 3, and Roman numeral 4 for quadrant 4. So let's complete the statements about ordered pairs in each of the 4 quadrants. So all points in quadrant 1 have x values that are positive or negative, and y values that are positive or negative. What would you put in each of those? So you're right, positive values and positive values. X values and y values are always positive in the first quadrant. So what about quadrant 2? If all of the points were over here, what x and y values would they have over there? Perfect. Negative x values and positive y values. All of those x values are always negative, and all of the y values are always positive. All right, so you know where we're going. So quadrant 3, what about all the points in quadrant 3? So they're both negative. All the x values are negative, and all of the y values are negative. All right, so here's one that's a little more difficult. In quadrant 4, what do we have? All right, so they're going to be positive and negative, so the x values are all positive and the y values are all negative. So that's the trait that you're going to notice for each of the 4 quadrants. Quadrant 1 is plus and plus, quadrant 2 is negative and positives, quadrant 3 is both negatives, and quadrant 4 is both positive and negative. Now you don't really have to memorize this, but it'll become very useful as you begin to make your own graphs to realize that there are certain quadrants in the Cartesian coordinate system that has different values. Now when you're graphing with many points, each point plotted on a graph is an ordered pair, an x value and a y value. So the relationship between x and y can become evident by the appearance of those dots. So here we have what looks like a straight line, this relationship. So as x gets larger and larger, y gets larger and larger. So you probably assume that the dots will continue upward. Now in this example, you'll notice that there's a downward trend and then an upward trend. And you can see that very clearly with the values. So it might not be so obvious in a table of values, but you can see it as a graph. Now here's a graph that shows what? That the y value stayed basically the same and doesn't change regardless of what x does. And here you plot some data points, and what do you think about that? Well, it's probably not very clear, is it? And that's also good information, because you may have thought that there was a relationship between x and y, and when you plotted it, you realize that there may not be a relationship between x and y. Maybe my cable got unplugged when I measured these things. So the graph is very helpful in learning how to read a graph is a very important skill as a photonics technician. Reading a graph is very important, so the first thing that you should do when you're reading a graph is note the labels on the axis. What are we graphing here? We're comparing temperature in degrees Celsius with temperature in degrees Fahrenheit. And which ones are the x values? X values are the Celsius temperatures, and the y values are the Fahrenheit temperatures. So the ordered pairs out here would be first the x value, as in 40, and next the y value, which might be 100. Next thing you need to notice is what is the units of measure for x's and y's. So in this case, we're graphing Celsius degrees, and y will be Fahrenheit degrees. Next, we should note what are the scales used to mark each axis. How much does each division represent? Well, we look at the scale markings, and it goes 0, and then we skip 1, and then 20, and then skip 1, and then 40, and so on. So each grid mark here represents what? 10 degrees Celsius. So if we had numbers next to every one of these grid marks, we'd have 10, 0, 10, 20, 30, 40, 50, and so on. So what about the vertical axes? A little different, isn't it? So we go 0, skip 1, and then 40, and then skip 1, and then 80. So each grid mark here would be 0, 20, 40, 60, 80. So there's a difference between the horizontal scale and the vertical scale. So is the scale the same in each? No, we've already observed that it's not. And where's the origin on this graph? Is it shown? The origin is where 0 and 0 are. And so the origin is actually right here and not over to the left. So we've actually shifted the origin because we're allowing for a negative value. So here's an example for reading a graph. We'll look at that Fahrenheit temperature graph. What Fahrenheit temperature corresponds to 20 degrees Celsius? Well, we observe the graph relationship between the F and C. That's the blue line. And we find 20 degrees C on the horizontal axis, and we follow that line up till you hit the graphed dot, and that'll be the x value for that dot. And then we need to find out what is the y value for that dot. and we move over to the y-axis, and we find out that it's about 70 degrees Fahrenheit. So for this graph, we would estimate that the ordered pair for that dot is 20 degrees Celsius and 70 degrees Fahrenheit. And how about the other direction? What's the Celsius temperature corresponds to 32 degrees Fahrenheit? Again, we would find 32 degrees Fahrenheit. This time it's going to be on the y-axis, and then we need to follow up the horizontal line across until we find the dot that's plotted there. And we determine what is the x value that corresponds to that. So we follow the vertical path down until we find, in this case, about 0 degrees C. This is just as we expected, right? So the ordered pair here would be what? 0, 32. 0 degrees Celsius, 32 degrees Fahrenheit, because you always put the ordered pair with x first and then y. So what if we wanted to read the graph for a temperature that didn't happen to have the dot there? Well, that's called interpolating. And what Fahrenheit temperature corresponds to 50 degrees Celsius? So this is an example that we can try interpolating. So we're going to find 50 degrees Celsius on the horizontal axis and move up just like we did before, this time until we hit the line, and we won't encounter the line this time. We're going to have the line that goes in between two dots, and which truly represents the relationship between Fahrenheit and Celsius. And we call this interpolating, and we find that the Fahrenheit temperature that corresponds to that is about 120 degrees Fahrenheit. So again, it would be 50 degrees Celsius and 120 degrees Fahrenheit. And similarly, what Fahrenheit temperature corresponds to 110 degrees Celsius? So how far does our line go? It only goes out to about 100. So sometimes you might need to have values that go beyond the graph, and that's called extrapolating. So when you extend the graph, that can be a little bit risky sometimes. So if we extend the line out and we follow the 110 degrees C vertical all the way up until you reach the extrapolated graph line, and then move over, and we have to estimate what the F will be. In this case, it'll be about 230 degrees Fahrenheit. And we'd estimate about 230, so the ordered pair for this relationship would be 110 Celsius, 230 degrees Fahrenheit. So we can also observe trends on this graph. So look at the titles and labels on this graph. So we're comparing what? Pressure versus time. And in this graph, it's not a straight line like the Fahrenheit and Celsius graph that we just looked at. So we're looking at pipeline pressure versus time. It shows a trend or pattern that might not be evident from just a table of values, but it looks like things are going downhill, doesn't it? So it looks like not only is the pressure dropping, but it also appears to be dropping faster in the afternoon as it did in the morning. So that's probably not a good sign for this pipe. Spotting trends like this is a common use for time graphs. Read the values from this graph just like we did before. So at 8 a.m., the pressure was 660 psi. And at 11 a.m., we have to interpolate a little, but we find that the pressure is about 648 psi. And what was the pressure at 6 p.m.? All right, so we're going to have to extend that line. So what is that called again? Extrapolating. So we're going to have to extrapolate the graph past 4 p.m. and predict the pressure at 6 p.m. So what does that look like? That doesn't look like you're quite as confident doing that. So who knows, it might have dropped a whole lot more, or it may have recovered and started to drop less. We just don't feel quite as confident in extrapolating this graph, and that's one of the dangers of extrapolating. So look at the general steps for drawing our own graphs. So the first thing that we should do is decide on a title for the graphs. So let's pick our data, which is going to be rainfall data. And we're going to pick a title for rainfall in April. So we look at our data and we have weeks and numbers of inches of rain each week. So that'll identify our two axes in our graphs. So we'll determine which one should be X and which one should be Y. So we're going to label week as the x-axis and rainfall as the y-axis. So we plot the ordered pairs one at a time, going over the x values and up the y values. And we'll draw a straight line or a curved line through the plotted points. So sometimes you draw a best fit line. Now, we can see a trend in this rainfall data. It simply is dropping off as the weeks went by and things warmed up and less rainfall came to this location. So here's another one given voltage and current measurements illustrating Ohm's Law as shown. Let's make a graph of the voltage and current ordered pairs. So a good title for this graph would be Ohm's Law. So since that's what we're showing, so the axes will be probably voltage from 0 to 50 and current from 0 to 5. We usually choose the independent variable as the horizontal axis, so we're going to guess that the person who measured this data turned up the voltage in 10-volt increments versus then the other way around. So that would make voltage the independent variable, the one that's being controlled, and current the dependent variable, which would be the one that would be on the vertical axis. So let's draw and label the axes on this graph. So Ohm's Law is our title, voltages in volts are our x-axis, and current measurements in amperes form our y-axis. So now we'll plot each of those points on the graph, and we'll start off with 0 and 0, 10 volts, and 1 amp, 20 volts and 2 amps, 30 volts and 3 amps, 40 volts and 4 amps, and finally 50 volts and 5 amps. And here we can probably line this up with a straight line to connect the dots, since this is a dependable relationship, since this is a good circuit, well behaved. Now, where's Ohm's Law in this graph? You'll remember Ohm's Law, voltage is equal to the current times the resistance. And we have the voltage and the current, but do we have the resistance on here? Well, we can rewrite that as I times R, or the current times resistance, equals the voltage V. And we can solve for I by dividing both sides by R, the resistance, and we get I is equal to 1 over R times V. And that happens to look a lot like a linear relationship that you may recall from your previous math classes, where y is equal to mx plus b. In this case, b is 0, the intercept, but we do have y is equal to something times x, some slope, that is, times x. And so the slope in our graph happens to be 1 over r, the inverse of the resistance. So since the slope is the change in y divided by the change in x, in this case, if you look at our line, we have the change in y is 2 amps and the change in x is 20 volts. That will be 2 amps is equal to 20 volts. And so the slope in our graph happens to be 1 over r, the inverse of the resistance. So since the slope is the change in y divided by the change in x, we have in this case, if we look at our line, we have the change in y is 2 amps and the change in x is 20 volts. That'll be 2 amps divided by 20 volts is equal to 0.1 amps per volt. And that's our slope for this line. And since the slope is equal to 1 over r, then r would be equal to 1 over the slope. And so you can put our slope value here down at the denominator. So we'll have 1 divided by 0.01, giving us a unit of 10, and then volts per amp, which just happens to be equal to 10 ohms. So sure enough, our answer for this circuit will be 10 ohms. And we found that out by measuring the slope for this graph. So now I think that we're ready to answer the opening scenario. We're going to first find how much laser power gets through the aperture when it's equal to the laser beam spot size. So when A is equal to W, the ratio of A over W is equal to 1. So let's locate the ratio of A over W equals 1 on the x-axis and move vertically up until you intercept the power transmission curve. From that point, you move left and you read on the y-axis about 0.86 or 86%. So about 86% of the laser powers will get through the aperture when the aperture is the same size as the beam spot. Now the next part of this question asks, what is the ratio for a pass-through of 50% of the beam power? Otherwise, what will be the portion of A to W when half of the power is blocked by that aperture? Well, to find that, we do the 50% mark on the y-axis. We find that, and we move across horizontally until we intersect the curve, and then we move down to read the value on the x-axis, so about 0.6. So 50% of the laser incident power, you will need to narrow the aperture to about 60% of the beam diameter. So instead of being 50%, it's about 60%. And the last thing that it asks us is, what is the minimum value of that aperture? So what's the minimum size of that aperture for which essentially all of the laser beam power will get through? And inquiring minds would like to know, so let's find out. So we'll locate 1 or 100% on the y-axis, and this time we'll move across until we reach the curve. And this time it's a little harder to figure out exactly where it reaches the curve, but this time we'll figure right about here, and then we will move down from that point and we come up with about 1.6. So when the aperture is about 1.6 as large as the beam diameter, all of the laser's power can make it through that hole. So that's a pretty interesting result, right? So let's take a look at some of the practice exercises. This is our chance to build up our confidence and see some real-world scenarios of problem solving with graphs and rectangular coordinates. So first one is given a graph of total highway mileage as shown here. So you're going to have to practice reading these graphs here. So what type of vehicle does this graph describe? So we look at the graph and we look at the legend and we see here that it's passenger cars and trucks and buses. So there's two sets of data on this chart. So the square little dots and the round little dots distinguish between the two types. So we have to look at that closely to distinguish which is which. And what span of time does this graph cover? Well, again, we look at the graph closely and we have two clues here. We have it in the title, and we also have it in the x-axis, which is the years for this data. So it's from 1945 to 1995 data. Next, which type of vehicle is increasing its annual mileage at a faster rate? So a faster means it's rising more rapidly, right? So it looks like the overall slope for the passenger cars is steeper than the trucks and the buses. So we would have to say that the passenger cars are increasing their mileage faster. Now it says estimate the trucks and buses mileage in 2000. So this is the issue of extrapolating, and this is a little iffy, as we know, predicting the future, but it looks like if things continue in the same trend as they have been, that the result will be about 550 billion miles, and that seems reasonable for the highway mileage traveled by trucks and buses in the year 2000. Exercise 2 is going to give us another chance to practice reading a graph. So this one has 3 relationships on it. So we're comparing crop yields to average temperature and rainfall, and which units are being used for the crop yields. Well, you can see from the y-axis, bushels per acre is being used, and the average temperatures, which is along the horizontal axis, the x-axis in degrees Fahrenheit. And it looks like 3 different graphs. We have 1 inch of rainfall, 3.5 inches of rainfall, and 6 inches of rainfall. So how can you identify the data from the 3 different rainfalls? What's the secret? So just like the previous graph, we have a legend or a key. And the key shows you that the 1 inch rainfall is a solid line with no bullets or dots on it. The 3.5 inch rainfall is a dashed line with no data points. And the 6 inch rainfall is a solid line with dots. Now, isn't it much easier to see all of that with the color that we've added here? So use your colored skills here when making your graphs if at all possible. You don't have to keep them black and white anymore. So the third part of exercise 2 shows that for an average temperature of 82 degrees, what crop yields can one expect with a rainfall of 6 inches, or for 1 inch? So let's first look at the 6 inches, and we'll go up the curve like we learned to do in this lesson, and we hit the data point, and we go across to the left, the y-axis, and we have about 75 bushels per acre when the rain is at 6 inches. Now for a 1 inch rainfall, we'll find 82 degrees Fahrenheit on the horizontal axis as we go up and over to 37 bushels per acre. Now for an average temperature of 70 degrees, do higher yields come from heavy rainfall or light rainfall? So we're going to go up from 70 on the horizontal axis and see which curve we encounter first. So the first curve is for 6 inch rainfall, a heavy rainfall based on a comparison here, and that yields about 42 bushels per acre. And if we go up next to the 3.5 inch rainfall, we get about 46 bushels per acre. And if we go up all the way to the top curve of 1 inch rainfall, we get about 62 bushels per acre. So the highest yields at cool temperatures came from the light 1 inch rainfall. Okay, so let's skip over to exercise 5. This will give you a chance to draw your own graph instead of reading a graph. And here we have a lab technician that's conducting a stress analysis on copper wire samples. The sample length is recorded under various loads as recorded in the table. So we have to construct a graph. So the first thing that we need to do is identify the axes, right, and the scales. So here we've done it. We've set up the load on the horizontal axis because that seems to be the independent variable, and the stretch in inches will be on the y-axis. And we scaled it so that it accommodates all of our data from 0 to 0.8. We'll in fact include all the data on our chart, and from 0 to 16 pounds we'll include all of our data. So now we're ready to start plotting our data. So here's 0 and 0, 2 and 0.02, 4 and 0.04, 6 and 0.06, 8 and 0.08, so we're not getting up very high, are we? 10 and 0.10, and 12 and 0.13, and 14, and whoa, that one went up a lot, 0.64, and we connected those with a line, and something looks pretty strange, doesn't it? So it looks like we've reached the load limit for this wire, and now we need to find the load for which wire will probably stretch to the point of breaking. So it looks like something's happening strange between 12 and 14 pounds of load. So it looks like that will probably be the load limit for that wire. So we wouldn't want to put anything stronger than 13 pounds on that wire. Alright, so can we estimate the stretch at 3 pounds even though we don't have a dot there? Well, we can certainly go up and hit the graph and go over to the left, and it looks like it's going to be close to 0.03. So what about 16 pounds? So for this one, we're going to have to extrapolate. So since everything here is happening really strangely, it doesn't really seem like it's going to be even a good idea to guess, because it could go straight up or flatten out. We don't really know. So extrapolating in this case is really not a wise idea. Alright, so that concludes our treatment of graphing and rectangular coordinates. So I now know that you have enough confidence to finish the rest of those practice exercises and get really good at drawing graphs and reading graphs and interpreting them. So good luck, and we'll see you next time.